All right, let's dive in. Today we're talking about something really cool at the intersection of statistics and computer science: graphical models. Now, I know that might sound a little intimidating, but trust me, it's a super powerful way to visualize and think about uncertainty. And you actually use it every single day without even realizing it. I mean, really think about it for a second. How on earth does your phone's voice assistant actually get what you're saying? Or how does your car's GPS figure out exactly where you are and where you're going, even when the signal isn't perfect? Our world is just filled with uncertainty and messy data. Well, the secret sauce behind all this incredible tech isn't magic. It's actually a brilliant concept, a kind of blueprint or a visual map for probability. It's a map that helps machines navigate all the complexities of our uncertain world. And that is exactly what we're going to explore today. So let's break this down. What exactly are these blueprints for probability? Well, at their core, they give us a surprisingly simple and kind of elegant way to represent really complex relationships. Okay, so the official term is a probabilistic graphical model, but all that really means is it's a picture that represents probabilities. You see those circles? We call them nodes, and each one stands for a random variable, which is just a fancy term for something you're not sure about, like, is it going to rain today? And the lines connecting them show how these things influence each other. The whole thing, the entire map, shows you the full picture of how likely all the different outcomes are. It turns complicated math into a diagram you can actually understand. Now, these models come in two main flavors. On one side, you've got directed graphs, which we call Bayesian networks. Here, the lines have arrows, which show a kind of cause and effect flow. You know, if it's cloudy, it might rain. One thing leads to another. Then on the other side, you've got undirected graphs, or Markov random fields. Here, the lines have no arrows. They just show a mutual relationship, like how a pixel in a photo is probably going to be the same color as the pixels right next to it. To really get a feel for this, let's look at a classic example of a Bayesian network, and we're going to tell a little story of cause and effect about something I think we can all relate to: exam stress. Okay, so check out this map. Each circle is a factor. B, up at the top, is whether the course is boring. Now, this directly influences R, whether you revise for the exam, and A, whether you actually attend the lectures. Then, both of those influence the final outcome, S, whether or not you're scared. You can see how the arrows clearly show that flow of influence. So, how does the map know how strong all these influences are? That's where these things come in: conditional probability tables. Every single node has one. This table right here is for the scared node. It shows you the probability of being scared based on whether you revised and whether you attended. So, for example, if you didn't revise but you did go to the lectures, there's a 60% chance you'll be scared. This is where the model stores all its knowledge. It's the brains behind the operation. All right, let's actually use it to predict something. All we have to do is follow the arrows. Let's say we know the course is boring. Well, the model knows that means you're less likely to attend the lectures. And if you don't attend, the probability table tells us that, yep, you're more likely to be scared. The graph just makes this whole chain of logic incredibly easy to follow. Now, that seems pretty simple, right? Just follow some arrows, look up some numbers. But here's the twist. Actually calculating this stuff perfectly, especially in a huge network, it's a process we call exact inference, well, it's unbelievably difficult. In fact, it's what's known as an NP-hard problem, which is just a fancy way of saying it's brutally, mind-bogglingly complex. To put that into perspective for you, if you have a model with just 10 variables, there are over 10 to the power of 18. That is 10 quintillion possible ways you could draw the arrows between them. So why so many? It's something called a combinatorial explosion. For every new thing you add, the number of possible connections doesn't just add up, it multiplies. Trying to find the one best map out of quintillions of possibilities it's astronomical. But hey, Bayesian networks are just one tool in this whole graphical model toolkit. Different problems need different kinds of maps. So what about problems where influence isn't just a one-way street? Or what about stuff that changes over time? Remember those other models we mentioned, the ones without the arrows? They're called Markov random fields, or MRFs, and they are perfect for situations where influence is local and mutual. It goes both ways. A perfect example is a digital image, where the color of any single pixel is super influenced by its neighbors, and it influences them right back. And this right here shows you their power. It's awesome. On the left, you've got an image that's totally corrupted with random noise. but by applying an MRF with one simple rule, that pixels next to each other really want to be the same color, we can recover the clean image you see on the right. The model just enforces that local consistency, and boom, the global picture just emerges. It's an incredible result from such a simple idea. Okay, so MRFs are great for things laid out in space. But what about data that's a sequence? Data that happens over time, like the words in a sentence, or even trying to guess what a student was up to last night just by seeing how they look today. For that, we have hidden Markov models, or HMMs. The best way to think about it is like you're a detective. You see the clues. We call those observations, like seeing a student who looks tired, but you don't know the full story. Those are the hidden states, like were they studying all night or were they partying? An HMM is like the detective's logic, piecing together the most likely story of hidden events that led to the clues you can actually see. So we've seen these different kinds of maps, for cause and effect, for images, for sequences over time, but why does any of this really matter to you? Well, because these elegant ideas have a huge real-world payoff, and chances are you're carrying it around right in your pocket. These maps of uncertainty, they're not just some theoretical toy for academics. They are the practical, powerful engines running quietly in the background of so much of our modern technology, helping our devices make smart decisions in a messy, uncertain world.
So where are these models hiding in plain sight? Well, the hidden Markov models we just talked about, they're the absolute backbone of speech recognition. The Kalman filter, which is another type of graphical model, is crucial for tracking in your GPS. They're used in genetics to understand how genes interact, in medicine to help diagnose diseases, and even in the error-correcting codes that make sure your texts and emails actually get through. They are a truly foundational technology.
Which leaves us with one final thought. The true power of graphical models is their ability to take a super complex, uncertain system and literally draw a map of it. A map we can use to reason, to predict, and to understand. So the real question is, now that we have this language for mapping uncertainty, what other complex systems, in economics, in climate science, maybe even inside the human brain, will we be able to map out and ultimately understand next?